Hi everyone, my name is Atesalp, and I'm a data scientist working at Giza. In short summary, what we do in Giza is that we build zKML solutions and similar verifiable machine learning solutions, as well as integrate them into Onchain, essentially. To quickly talk about what I'm going to do in this presentation is, first of all, I'm going to introduce our POC model, which is essentially a AI model. I wouldn't say it's like a complex AI model, but it's a POC model that is meant to showcase how we can implement machine learning on-chain, as well as then talk about how we do proving methods and essentially how we can improve what we already have in terms of zKML. So this is the QR code for the repository. I'm going to give you a few seconds if you want to take it. So what is the repository that I'm going to introduce today? It's essentially a POC model of a Tic Tac game. I think everyone knows how it's played. They're like 3-to-3 matrices, and you play to essentially create a row of the same symbols. It's very similar. It's also very simple. And the idea is that it's very easy to create a model or an agent that you can play with it. And I'm first going to quickly explain how the model is developed. As you can see, it's in Python. What you see is, I think it's quite explanatory. It's a 3-to-3 NumPy array, and we have some additional functions that sort of play with it. In terms of game design, what you see is essentially, first of all, what we do is we generate all the possible moves, right? And then we use a model, a Python model, a PyTorch model in specific, that sort of tries to find the best move that has the highest chance of winning. As you can see here, it's a 61 parameters, so quite low. It's not a complex model, but it's supposed to be like that, I guess. So how we apply machine learning in our code is that we have a move selector. We first find out all the possible moves, and then using the Tic Tac agent, try to find the optimal move to play against it. Okay, now we have the model, but next question is, how do we use zKML to make sure that that agent can play the game on-chain? For that, we use Orion. Orion is an in-house library that we use that is built on top of Cairo, which is a provable, generalized, Turing-complete language, and we build our sort of library, the Orion library, on top of it, that is meant to specialize in arrays and like essentially all the machine learning specific operations that happens all the time in big PyTorch models or whatever. Focusing on the individual libraries, we have the number library that is actually very important because numbers in machine learning are not just numbers, but also tensors and arrays. And this is meant to be sort of like a supporting library for the tensor library, which is meant to implement arrays in Cairo. And then we have the ML-lib and the NN-lib. Machine learning lib is more specific for simpler machine learning models, such as linear regression, whatever. And then libraries are specific for more complex neural networks or deep networks. So we have the model, and then we use the Giza CLI to convert it into an Orion package. What are we looking at? We're looking at, first of all, the crates and then the source code. As you can see, so our model had 3 layers. That means that for each layer, we have the biases as well as the weights. That means we have 6 weights. And we have the inference, library, and test that are supposed to integrate all the different inferences as well as the weights to essentially create the inference on-chain. Coming to weights, this is what you've find in a specific weight file is you find something like this, where I just want to quickly show some interesting details about this. First of all, we just have array. We don't currently have matrices because they're not implemented in Cairo. So we have all the data as a one-dimensional array, but on top of it, we have the shape. Then using files like that, we create the inference. So if we go to right side, this is essentially using Onyx, which is a language agnostic machine learning interpretation and representation. We can see what the operations look like inside a model. So this is how an inference is done, taking the input and then coming up with the output. This is essentially that transpiled with our Orion library into Cairo language. Here you can see all the different operations that happen here. You can see the operations also in there using our library. And then coming to the metrics, I think this is the most interesting part. We have actually implemented the POC and we have run it on-chain. You can see the benchmarks here. There are some interesting things to talk about, I believe. First of all, what you're going to realize is the Cairo virtual machine execution time is 1 second and verification time is also really, really small. But what's actually quite big is the proving time. This would obviously be a problem. Like if you were to play a Tic Tac Toe against an agent, you wouldn't like to wait 1 minute essentially for the agent to answer your move. But this isn't a problem because we can run the proving asynchronously. So we just need the execution rather than the proving, and then the proving can be proven later on. That being said, one thing that I want to sort of show is that this method is naive. That means that all the inferences and all different operations that we have seen in the computational graph is actually done on-chain. Is there a better way to do that? We think so. So coming to more optimized way of doing things, and by the way, this isn't only to make it more efficient, this is also to be able to host more complex models. So this looks a bit complex, so I'm gonna take my time to explain everything. What you see here is not a 3-layer model, but a 6-layer model. But what happens is that rather than coming up with this huge inference graph, we essentially do a recursive proving of each layer, where we compute layer 1 to layer 2. So this would take as input the input of the model, and as output, this would give the output that you would expect from the layer 2. And we only create a proof of that layer. We also do the same operation for L3 and L4 and L5. And then using the input and the output of these layers, as well as as you can see here, the verification of the proofs, we create a different proof. So this looks a bit complex. What we're doing essentially is that we're assuming that the verification of the proofs on their own is actually a computation, and we're creating a proof of that computation. This also happens with layer 3, layer 4 proof, and layer 5 and layer 6 proof. So we create this tree that we can recursively prove over and over again. What we have at the end is just a verification of the A and the B computations. What does that mean? That means that our proof at the end is much smaller. It's not the proof of all the different layers, it's just the proof of the verification. Additionally, something that we utilize, which I think is an awesome invention, is that we use MLIR, which is a really fast way to compute inferences, but unfortunately isn't provable, to find out what the output of layer 2 and what the output of layer 4 would be without actually running the proving time. What that allows us to do is that we can parallelize what happens. Yeah, what we can do is we can parallelize all these different provings in different containers. So rather than waiting for L1, L2, L3, L4, we can run L1 to L2, L3 to L4, and L5 to L6 on their own. So thanks a lot. My friend Rafael actually implemented the code. I'm just taking his place because he couldn't come. So if you have any questions, he would actually love for you to write to him. But yeah, thanks a lot.